potential, and that is elastic potential energy. Elastic potential energy is stored energy in a spring or spring-like object. The force that we're going to use is the spring force. This comes from Hooke's law, but we're not really going to get into Hooke's law very much. Okay, you just need to know the equation. That's given right here. So the force is K times the displacement, which is delta X. And you can have vertical or horizontal displacement. It's allowed. You'll just treat the delta Y as a delta X. Okay. The potential energy is found by doing 1/2 times the K times delta X squared. And you're wondering, what is K? K is the spring constant. It's basically a specific number based on what material you're using, whether it's a thin rubber band, thick rubber band, a thick spring, a loose spring. Just depends on the object itself. Every object has its own unique spring constant. Your delta X is going to be how far you stretch or compress that object. Some things can be compressed or stretched, right? Springs can be either or. You have bungee cords, you have rubber bands, you have an elastic waistband, you have all kinds of objects that fall into this category. Remember that in order for it to be elastic, once it's stretched or compressed and you let go, it goes back to its resting state and it looks the same as it did before you stretch or compress it. Okay, if I stretch something that is not technically elastic, like silly putty, right? It will stay stretched. It will not return to its original form. So therefore, it would not fall into this category or follow these elastic rules. So the first example is asking how much force is necessary to stretch a spring with a spring constant of 600 newtons per meter. So that's our first given, okay? And it's giving us a displacement of 0.5 meters. Find the force of that spring. It's pretty easy. Remember, forces are measured in newtons. So the first problem is an example of how to use the first equation. The second example is using the second equation. A spring compressed by 0.10 meters, which would be 10 centimeters in case you were wondering. Stores 300 joules of potential energy, elastic potential energy. It says, what is the spring constant? We are looking for K. So we're using the potential energy elastic. We cannot use the force equation because we do not have, I'm not looking for force. I don't have the force, okay? Don't have enough information to use the force equation in order to find K. So we need to use the potential equation. Make sure you're plugging the information to the correct location variable in the equation. Simplify, divide. K is going to be 60,000. Yes, that is a large number, and that's okay. So what did I stretch my rubber band for? what happens when I stretch my rubber band and then let it go? Well, I stretch my rubber band. If I were to let go, right, it goes back to its resting position. But if I actually like let go, it moves. I know. Oh my God, let's go back. I've never seen it in my life. No, I know you know that, okay? But I want you to think conceptually now, how much potential energy does it have? Once I let go, it's no longer stretched. It's not at rest. So how much potential does it have? Zero. It doesn't have any potential anymore. I let go. It moved. All that potential that I had when I stretched it is transferred into kinetic. Just like when you guys were using the rubber bands for your cars. We took that energy and turned it into kinetic energy to get the car to move. That was the whole point, right? I want you to keep those in mind. Those are the trickier questions.